Forecasters are warning that this year's extreme El Niño could hit the United States hard, reshaping storms, rainfall, heat, flooding, and winter weather from the Pacific coast to the east. This is not just a distant ocean pattern. It begins in the warm waters of the tropical Pacific, then moves through the atmosphere, guiding winds, clouds, and storm tracks across the country. In this video, the journey follows how one powerful climate signal can reach homes, roads, farms, and cities. Before it begins, please like this video, subscribe to the channel, and stay with the story as the warning slowly unfolds. Around Earth, the air forms a deep and restless shell, held close by gravity and warmed unevenly by sunlight. It is thin beside the size of the planet, yet it carries the conditions known as weather. During a year when forecasters watch for a strong El Niño, this outer shell becomes the first broad region to observe. El Niño is a natural climate pattern linked to unusual warmth in the tropical Pacific, but its influence is not confined to one ocean basin. It reaches the atmosphere through heat, moisture, and pressure, and the atmosphere spreads those signals across long distances. The first view is planetary, from space. The atmosphere has no sharp edges. Clouds curl in white bands, storms turn over ocean and land, and dry zones appear where sinking air limits rainfall. The equator receives more direct sunlight than the poles, so the air system is always reducing an imbalance. Warm air expands and rises, cooler air sinks and spreads. The result is not a simple flow from south to north or north to south, because Earth rotates. Rotation bends moving air, shaping broad belts of wind and pressure. These belts are not fixed lines. They shift with seasons, with ocean temperatures, and with patterns that develop over weeks and months. In an ordinary year, the atmosphere already contains many layers of motion. In the middle and upper troposphere, the lowest major layer of the atmosphere, broad currents steer storm systems. The troposphere is where most clouds and weather form. Its depth changes from place to place, rising higher in the warm tropics and lowering toward the cold poles. Above it, the stratosphere lies more stable and dry, with slow circulation and a different temperature structure. The main story of El Niño weather remains mostly within the troposphere, where water vapor and heat are active. Forecasters begin with measurements across this global air shell. Satellites track cloud tops, water vapor, temperature, and winds. Weather balloons rise through the lower atmosphere and record pressure, humidity, and wind direction. Computer models use these observations to estimate the present state of the air and then calculate likely changes. A forecast is not a single promise. It is a range of possible outcomes based on physical laws, present measurements, and patterns seen in past events. When forecasters warn that an El Niño could become extreme, they are describing a risk that the atmosphere may organize around a powerful source of tropical heat, while the final strength remains uncertain. The atmosphere responds to El Niño because air and sea exchange energy continuously. At the outer planetary scale, the first sign is not one storm or one flooded street. It is a rearrangement of temperature and pressure patterns. Warmer tropical waters can release more heat and moisture into rising air. Rising air lowers pressure near the surface and helps build tall cloud regions. Elsewhere, air must sink to balance that rise. This creates broad changes in circulation, meaning the large-scale movement of air. Circulation connects distant regions without requiring a single storm to travel from one place to another. Instead, the whole air shell adjusts, like a wide fabric lifted in one area and lowered in another. The atmosphere contains waves, pulses, and repeating patterns. Some move around the globe in days, others persist for weeks. El Niño can influence these patterns by shifting where heat is released in the tropics, in the atmosphere. Heating is not only warmth measured by a thermometer, it is also latent heat, the energy released when water vapor condenses into cloud droplets. Tropical cloud towers can release large amounts of this energy high above the surface. That release changes pressure and wind at altitude, and those changes can spread outward through the flow. Over the United States, the atmosphere does not simply receive an El Niño signal in a uniform way. The country stretches across many latitudes, landforms, and climate zones. Air moving over the Pacific reaches the west coast after crossing a long ocean. Air over the Gulf of Mexico can bring warmth and moisture northward. Cold air can still move from Canada. Dry air can still settle over interior regions. El Niño changes the odds of certain patterns, but it does not erase all other sources of variability. Observations indicate that stronger El Niño events often increase the chance of wetter conditions across parts of the southern United States during the cool season. While some northern areas may lean warmer, it remains uncertain exactly where the heaviest storms form in any given year. At the outer level, the phrase extreme El Niño describes the strength of the climate pattern, not a guarantee that every place experiences extreme weather. The atmosphere translates the pattern unevenly. Cities experience heat through pavement, buildings, and local wind. Rivers respond only after precipitation falls across their basins. A strong climate signal can raise the likelihood of hazards, yet local outcomes depend on timing, storm tracks, soil moisture, snowpack, tides, and existing vulnerabilities. Scientific caution keeps these parts separate, so that a broad forecast does not become a claim about every neighborhood. The global air shell also sits within a warmer long-term climate. Human-caused warming adds heat to the atmosphere and ocean, raising the background on which natural patterns occur. This does not mean every El Niño impact is stronger in the same way everywhere. It means that some ingredients, such as atmospheric moisture, are changing. Warmer air can hold more water vapor, and that can support heavier precipitation when storms have enough lift and moisture supply. Heat records can also become more likely when natural warming patterns align with the long-term trend. The atmosphere is therefore carrying both natural variability and persistent change at the same time. In this first outer region, the main feature is connection. Air has no borders at coastlines or state lines. It moves in broad currents, rises and sinks in great cells, and carries water in invisible vapor before clouds appear. Forecasters watch these motions because an El Niño year can make the usual pathways bend toward different probabilities. The warning begins here, not with panic, but with attention to a planetary system measured every day. The outer shell of air remains familiar in its daily winds and clouds, yet it is sensitive to shifts in heat below. Its large patterns set the stage for how an El Niño signal may pass from the wide planet toward the regions where people live. Across the planet's surface, the oceans form the broadest moving store of heat. They cover most of Earth and absorb sunlight through their upper layers, while winds, waves, and currents spread that heat across distance. In an El Niño year, the global ocean surface becomes the next region of attention. It is wider and slower than the atmosphere above it, but it is closely linked to every passing wind and every change in cloud cover. The ocean does not respond as quickly as air, because water is dense and holds heat with great capacity. Once unusual warmth gathers across a large basin, it can last for months and influence the atmosphere above it in steady ways. The surface of the ocean is never still. It rises and falls with waves, shifts with tides, and moves in broad currents shaped by wind and Earth's rotation. Sunlight warms the upper ocean, while evaporation removes heat and adds water vapor to the air. Rainfall freshens the surface. Dry winds increase evaporation and can make the surface saltier. These exchanges form a thin but important boundary between sea and sky. During El Niño, forecasters pay close attention to this boundary, especially where warmth at the surface becomes widespread enough to change the pressure and wind fields above it. Globally, the oceans do not warm evenly. Tropical waters receive intense sunlight and often remain warm through the year. Mid-latitude waters change more strongly with the seasons. Polar waters hold more ice and are shaped by cold, darkness, and mixing. Ocean currents connect these zones over long periods, but the surface patterns seen in any single year depend on winds, storms, and deeper layers. A strong El Niño begins as a regional change in the tropical Pacific, yet the global ocean surface provides the surrounding context. Other basins may also be unusually warm or cool, and these conditions can either reinforce or complicate atmospheric responses. The ocean surface stores heat in the upper layer, where sunlight can penetrate and waves can mix water downward. This mixed layer may be shallow in calm tropical areas, or deeper where winds and storms churn the water. When the mixed layer is warm, the air above it can gain heat and moisture. When it is cool, the air above it is often more stable. Stability means that air resists rising. Warm water tends to weaken that resistance by warming the air near the surface and increasing evaporation. Moist, warm air is more likely to rise when other conditions support upward motion. In this way, the ocean surface helps decide where large cloud areas can develop. El Niño belongs to a larger pattern called the El Niño Southern Oscillation. This term describes linked changes in tropical Pacific sea surface temperatures and atmospheric pressure. The warm phase is El Niño, while the cool phase is La Niña. In the warm phase, the usual pattern of warmth in the tropical Pacific changes enough to affect rising air and rainfall. The ocean surface is central because the atmosphere does not respond strongly to hidden heat unless that heat reaches the boundary where air and water meet. Forecasters therefore measure sea surface temperature with satellites, ships, drifting instruments, and fixed buoys. The global ocean surface also reflects long-term warming. Observations show that oceans have absorbed much of the excess heat added to Earth's climate system. This stored heat raises the background temperature of many surface waters. An El Niño event occurs within that warmer background. It remains uncertain how every regional impact changes as the climate warms, because natural variability still shapes the timing and placement of storms. Yet a warmer ocean can supply more heat and moisture where atmospheric patterns allow. This makes the condition of the global ocean surface important even before focusing on the Pacific center of the event. In a strong El Niño year, maps of the ocean surface often show a broad ribbon of unusual warmth in the tropical Pacific, but the rest of the ocean matters too. The North Pacific may hold warm or cool patches that affect air moving toward North America. The Atlantic may influence moisture available to storms along the eastern side of the United States. The Gulf of Mexico can provide warmth and humidity to weather systems crossing the southern states. These regions do not create El Niño, but they shape the background through which El Niño-related circulation passes. The global ocean surface is therefore a field of interacting signals rather than a blank setting. Heat exchange at the surface depends on several quiet processes. Evaporation removes energy from the ocean and places water vapor into the air. Sensible heat transfer moves warmth directly between the ocean and the air when their temperatures differ. Long-wave radiation allows the ocean to lose heat upward. While sunlight adds heat during the day, clouds can reduce incoming sunlight and winds can increase evaporation. When large areas of ocean become warmer than usual, These exchanges can shift the energy supply to the atmosphere. The effect is not instant, but it can persist long enough to influence seasonal patterns. The ocean also remembers past winds. When winds push surface waters, they do not simply move in the same direction as the wind. Earth's rotation causes the moving water to turn, and layers beneath the surface respond as well. This can lead to broad changes in where warm water gathers. The surface pattern visible during El Niño is partly the result of earlier wind changes and waves moving through the ocean interior. At the global surface scale, the ocean appears smooth on maps, but it carries the memory of months of motion. Forecasters describe ocean surface anomalies, meaning departures from average conditions for a specific place and season. An anomaly is not the absolute temperature of the water. It is how different the water is from what is usually expected there at that time of year. This matters because tropical water is naturally warm, while higher latitude water is naturally cooler. A small anomaly over a large area can still represent a large amount of heat. A large anomaly in a key tropical region can have strong effects because it sits under air that is already close to rising and forming clouds. The United States is affected by ocean surface conditions through the atmosphere, but the oceanic setting is still essential. Storms that approach the west coast have crossed the Pacific and have drawn energy from the sea and air along their path. Rain systems that affect the south may draw moisture from nearby warm waters. Coastal flooding can be shaped by storm winds, waves, tides, and sea level during a strong El Niño. These effects depend on how the ocean surface guides the air above it and how that air later organizes into storms. In this second region, the scale remains broad and outward. The focus rests on the skin of the world ocean as a whole, with its slow heat storage and steady exchange with the air. The surface is not merely a passive mirror of the atmosphere, it is an active partner, taking in sunlight, releasing moisture, and holding warmth long enough to shape seasons. An El Niño warning gains meaning because the ocean can sustain a pattern after daily weather changes have passed. The wide global ocean surface is therefore the calm, deep foundation beneath the moving air, carrying heat across months and offering the atmosphere a change source of energy. Along the equator in the Pacific Ocean, a long belt of water stretches between the coast of South America and the islands and seas of the western Pacific. This region is central to El Niño because it lies beneath some of the most active exchanges between ocean and atmosphere on Earth. Sunlight is strong through the year. The difference between day length and night length remains smaller than at higher latitudes. The surface water is usually warm in the west and cooler in the east. But during El Niño that balance changes. Warmth spreads farther east than usual, and the equatorial belt becomes a broad source of heat and moisture for the air above it. The equator is a special place for ocean motion. Earth's rotation affects moving water and air differently on either side of it. North of the equator, moving flow bends one way. South of the equator, it bends the other way. Near the equator itself, this bending effect becomes weak, so winds can push surface water in ways that are distinct from higher latitude oceans. The usual tropical Pacific pattern depends on steady easterly trade winds, which blow from east to west across the basin. These winds help pile warm surface water toward the western Pacific and allow cooler water to rise in the east. During El Niño, the belt changes because those usual winds weaken or shift for a time. At this stage, the focus remains on the equatorial Pacific as a broad surface region, rather than on the deeper layers below it. The warm belt is not a narrow line, but a zone that extends several degrees north and south of the equator. Scientists divide it into monitoring regions to track sea surface temperature changes. These regions allow forecasters to compare present warmth with long-term averages. When the central and eastern equatorial Pacific remain warmer than average for long enough, and the atmosphere responds in a connected way, El Niño conditions are considered present. The strength of the event depends partly on how warm the surface becomes and how widely the warmth spreads. In normal conditions, the western equatorial Pacific holds some of the warmest ocean surface waters on the planet. This warm pool supports rising air, heavy tropical rainfall, and deep cloud formation. Farther east, near the central and eastern Pacific, surface waters are often cooler because winds and ocean motion help bring colder water closer to the surface. This east-west contrast is a key part of the tropical Pacific climate. During El Niño, the contrast weakens. The warm water does not remain as strongly concentrated in the west. Instead, it reaches into the central and eastern basin, changing where the air is most likely to rise. The change is important because the atmosphere above the tropical Pacific responds to where the warmest water sits. Warm water increases evaporation, placing more water vapor into the lower air. When moist air rises and cools, water vapor condenses and clouds grow. The release of latent heat during condensation helps strengthen rising motion. If the warmest water shifts eastward, the main area of tropical cloud formation can also shift. This does not mean clouds form everywhere along the equator at once. It means the region most favorable for persistent convection, or deep rising cloudy air, moves away from its usual position. The equatorial Pacific belt is watched by a network of instruments. Satellites measure sea surface temperature and cloud patterns. Moored buoys record wind, air temperature, humidity, and ocean temperature near the surface. Drifting floats and ships add measurements. These observations help identify whether the ocean and atmosphere are acting together. A warm ocean surface alone is not enough to describe the full event. The atmosphere must also show a related response, including changes in pressure and wind across the tropical Pacific. This coupling, meaning linked behavior between ocean and atmosphere, is what allows El Niño to influence weather far beyond the tropics. The central and eastern equatorial Pacific become especially important during a strong event, when surface temperatures there rise well above average. The heat source beneath the atmosphere is displaced across a very large area. The ocean does not need to be hot in an absolute sense compared with the western warm pool. It needs to be warmer than normal for that region and season. The air above these waters is adapted to usual patterns. When the surface becomes unusually warm, the balance of rising and sinking air changes. Pressure can fall in places where warmth encourages rising motion, while pressure can rise where air sinks more strongly. The coast of South America forms the eastern boundary of this ocean belt. In usual years, cooler water near the coast supports rich marine ecosystems because upwelling brings nutrients from below. Upwelling means the rise of deeper water toward the surface. During El Niño, warmer surface waters can reduce this process in parts of the eastern tropical Pacific. The immediate focus for the United States remains atmospheric, but the oceanic change begins here as a major disruption in the tropical Pacific's usual state. It shows how one belt of water can alter both marine conditions and atmospheric behavior. Across the equatorial belt, warmth spreads through waves and currents. Some waves are not the breaking waves seen at shore, but broad movements within the ocean that change sea level and temperature structure over great distances. Near the surface, warm water can move eastward when wind patterns allow it. These motions help maintain the surface warmth that forecasters monitor. The pattern develops over months rather than minutes. It is observed as a persistent change in the ocean, not as a single brief episode. The term extreme, when applied to El Niño, generally refers to the strength and extent of warming and to the degree of coupling with the atmosphere. Historical events show that very strong El Niño episodes can alter rainfall and temperature patterns across many regions. Still, each event has its own structure. Some warm most strongly in the eastern Pacific, others peak more in the central Pacific. These differences matter because the location of the warmer surface waters affects where tropical heating enters the atmosphere. Scientific forecasts therefore examine not only whether El Niño exists, but where the main warmth is concentrated. Within the equatorial Pacific belt, the surface water acts as the central source of the climate signal. It does not send a message in a simple line to the United States. Instead, it changes the pattern of tropical heating, and the atmosphere responds by reorganizing broad circulation. The effect is gradual and probabilistic. It changes the chances of certain seasonal outcomes, especially during the cooler months in North America. Forecasters study this region because it is where the physical basis of the warning becomes measurable. This third region is narrower than the global ocean surface but still vast. It is a warm equatorial corridor, bright under steady sunlight, crossed by winds and watched by satellites and buoys. In a strong El Niño year, its surface becomes less like the usual east-west contrast, and more like a widened field of unusual warmth. That warmth changes the air above it in ways that can travel through the global circulation. The belt remains oceanic, quiet in appearance, and powerful in consequence. It is the central source region, where the broad planetary concern begins to take a more defined shape. Above the equatorial Pacific, the trade winds form a near-surface layer of moving air. These winds usually blow from east to west across the tropical ocean, guided by pressure differences and shaped by Earth's rotation. They are not constant in every hour or every place, but their long-term presence helps organize the tropical Pacific. In ordinary conditions, they push warm surface water toward the western Pacific and help maintain cooler water near the eastern side of the basin. During El Niño, this wind layer weakens or changes, and the surface ocean begins to lose part of the pattern that normally holds it in place. The trade winds are part of a larger tropical circulation known as the Walker circulation. This circulation describes the broad east-west overturning of air along the equatorial Pacific. In its usual form, warm water in the west supports rising air and rainfall, while cooler water in the east favors sinking air and drier conditions. Air moves westward near the surface and returns eastward higher in the atmosphere. This is a simplified picture of a system that varies with seasons and weather, but it explains why the near-surface winds matter so much. They are the lower branch of a great atmospheric loop. In an El Niño year, pressure patterns across the tropical Pacific shift. The pressure difference between the eastern and western sides of the basin becomes weaker. With less pressure contrast, the trade winds weaken. Sometimes they pause for short periods. Sometimes wind bursts from the west move across parts of the equatorial Pacific. These westerly wind bursts do not need to last long to matter. They can disturb the surface ocean and help move warm water eastward. The ocean and atmosphere then begin to reinforce each other. Warmer water in the central and eastern Pacific encourages rising air there, and this rising air can further weaken the usual trade wind pattern. This feedback is one reason El Niño can grow from a developing disturbance into a basin-wide event. A feedback is a process in which a change supports more of the same change. In this case, weaker trade winds allow warm water to spread eastward. The warmer eastern and central surface waters change where air rises. The changed rising motion weakens the east-west pressure pattern that supports the trades. The weakened trades then allow still more warmth to remain or move eastward. The process is not automatic or endless, because other seasonal and oceanic factors can limit it. but it helps explain how a strong El Niño develops. The near-surface wind layer also controls evaporation. Stronger winds increase evaporation by moving moist air away from the ocean surface and replacing it with drier air. Weaker winds can reduce this cooling effect in some areas, helping the surface remain warm. The relationship is not the same everywhere because cloudiness, sunlight, rainfall, and ocean mixing also matter. Yet the wind layer is one of the main ways the atmosphere touches the ocean. It drags across the surface, transfers momentum, and changes how quickly heat leaves the water. Momentum is the tendency of moving matter to keep moving. When wind blows across the ocean, it gives some of its momentum to the water. This creates surface currents and can help pile water toward one side of the basin. Under normal trade winds, warm surface water is pushed westward. Sea level in the western tropical Pacific can stand higher than in the east because water has been pushed and stored there. During El Niño, weaker winds reduce this piling effect. The surface slope across the basin relaxes, and warm water can extend eastward more easily. This change at the surface begins with the wind layer pressing less firmly on the sea. The trade winds do not weaken evenly everywhere at the same time. Some areas may experience calm conditions while others still have easterly flow. Short bursts of wind can travel across the equator and alter the ocean's surface. Weather systems in the tropics, including clusters of thunderstorms, can disturb the trades for days or weeks. These shorter events are embedded within the seasonal climate pattern. Forecasters watch them because they can either support El Niño growth or interrupt it. A strong event often contains repeated wind disturbances that help sustain the change in ocean temperature. The atmosphere above the trade wind layer also responds. When surface winds weaken, the usual pattern of low-level convergence shifts. Convergence means air coming together near the surface. Where air converges, it often rises if enough moisture and warmth are present. In the western tropical Pacific, normal convergence supports deep clouds and rainfall. During El Niño, the zone of convergence can move toward the central or eastern basin. This movement does not happen as a single clean line. It appears as shifting cloud clusters, changing rainfall zones, and altered pressure patterns across the ocean. The weakening trade winds also change the exchange of carbon dioxide and other gases between ocean and atmosphere, though this is not the main reason forecasters watch them for United States weather. The tropical Pacific is a large area of ocean-atmosphere exchange. Changes in upwelling, temperature, and biological activity can affect how gases move across the surface. These processes are measured by researchers, but the immediate seasonal concern remains the wind-driven reorganization of heat and moisture. The near-surface winds are the hinge between the ocean's stored warmth and the atmosphere's broad circulation. Instruments over the equatorial Pacific record these winds continuously. Buoys measure wind speed and direction at the ocean surface. Satellites infer surface winds from the roughness of the sea, because stronger winds create different patterns of small waves. Reanalysis systems combine observations with weather models to estimate the full wind field. These tools allow forecasters to see whether the atmosphere is behaving in a way that matches El Niño. A warm ocean surface without the matching wind response may be less effective at producing broad climate impacts. A coupled ocean and atmosphere pattern carries more influence. The trade wind layer is also where uncertainty begins to matter in practical forecasts. Small differences in tropical winds can lead to different outcomes for the ocean surface. The timing of wind bursts can affect when warming grows or weakens. The location of weakened trades can influence whether the strongest warming appears in the central or eastern Pacific. Because the atmosphere is always variable, forecasters use many model simulations rather than relying on one path. The warning about an extreme El Niño reflects a range of evidence, not a single measurement. For the United States, the trade winds themselves are far away, but their weakening helps set the climate pattern that later influences storm tracks and rainfall probabilities. The winds do not carry storms directly from the equator to North America. They alter the tropical heat source, and the atmosphere responds through larger waves and pressure changes. In this section, the focus remains on the wind layer itself, where the ordinary easterly flow loosens and the ocean surface is allowed to shift. The fourth region is therefore a moving band of air just above warm water. It is simple in appearance, a steady push across the sea, yet it holds a central role in the El Niño process. When that push weakens, the tropical Pacific becomes less restrained by its usual pattern. Warm water spreads, pressure changes, and the rising zones of cloud begin to adjust. The near-surface trade winds mark the place where air first releases its grip on the ocean, allowing the larger climate signal to grow within the equatorial belt. At the very top of the ocean, a thin boundary forms where sunlight, wind, and evaporation meet. This boundary is often called the ocean surface or the ocean skin. Even though it is not a solid layer, it is a shallow region where temperature can change over a small depth, sometimes within a few meters, and where the exchange of heat and moisture with the atmosphere is most direct. During an El Niño year, this surface layer becomes a clear indicator of change, because it is where unusual warmth can be measured and tracked across wide distances. Sea surface temperature is the primary quantity observed in this layer. It describes the warmth of the ocean's uppermost water, usually averaged over a small depth to reduce short-term fluctuations. Satellites provide a global view by detecting thermal radiation from the ocean surface. Instruments on ships and buoys offer direct measurements that help confirm and refine these observations. Together, they show how the surface warms or cools compared with average conditions for a given time of year. An anomaly, or departure from the average, is often more important than the absolute value, because it reveals where the ocean is behaving differently from its usual state. During El Niño, the ocean skin across the central and eastern equatorial Pacific often becomes warmer than average. This warmth is not uniform. It can appear as patches that grow and merge over time, forming a broader region of elevated temperature. The spread of this warmth is influenced by earlier wind changes and by the movement of water within the basin. Once present, it can persist because the ocean holds heat more effectively than air. The surface layer is therefore both a signal and a source. It shows where warming has occurred and provides the energy that can affect the atmosphere above. The ocean skin also controls evaporation, which is the process by which water changes from liquid to vapor and enters the air. Warmer water tends to increase evaporation, all else being equal, because more molecules have enough energy to escape into the atmosphere. Wind speed, humidity, and cloud cover also influence this process. When evaporation increases, the ocean loses heat, but the atmosphere gains water vapor. This added moisture can support cloud formation if the air rises and cools. In this way, the temperature of the ocean skin affects not only heat exchange but also the availability of moisture for weather systems. Clouds above the ocean can, in turn, affect the surface temperature. Thick clouds can reduce the amount of sunlight reaching the water, limiting daytime warming. At night, clouds can reduce heat loss by trapping outgoing radiation. The balance between these effects depends on cloud type, thickness, and duration. During El Niño, changes in cloud patterns over the tropical Pacific can alter how much sunlight reaches different parts of the ocean surface. These changes can reinforce or modify the temperature anomalies already present. The ocean skin and the cloud field are therefore linked in a continuous exchange. The ocean surface is also shaped by mixing. wind-driven waves stir the upper layer, blending warmer water at the top with slightly cooler water below. When winds are strong, this mixing can deepen the layer of nearly uniform temperature. When winds are weak, the surface can become more stratified, meaning that warmer water remains concentrated near the top. During El Niño, periods of weaker trade winds can reduce mixing in some regions, allowing the surface to retain warmth. In other areas, storms or wind bursts can increase mixing and temporarily reduce surface temperatures. The pattern is not fixed, but the general tendency toward warmth remains where the broader conditions support it. Another feature of the ocean skin is its interaction with rainfall. Heavy rain can cool the surface slightly by adding cooler water and by enhancing mixing as raindrops disturb the surface. It can also reduce salinity, meaning the concentration of dissolved salts in the water. Lower salinity can influence density and mixing, though the effect is often modest compared with temperature. In El Niño conditions, rainfall patterns shift across the tropical Pacific, so the distribution of these local effects changes as well. The overall temperature pattern, however, is controlled by larger-scale processes rather than by any single rain event. The ocean skin responds to sunlight that varies with the time of day and with cloud cover. In the tropics, sunlight is strong and relatively consistent through the year, but daily cycles still matter. The surface can warm during the day and cool at night, creating a small diurnal cycle in temperature. This cycle is usually shallow and short-lived, but it can be more pronounced when winds are light and skies are clear. During El Niño, the broader warming signal is superimposed on these daily changes. Forecasters account for this by using averages that smooth out short-term variations, focusing on the sustained anomalies that influence the atmosphere. The connection between the ocean skin and the atmosphere is immediate in physical terms. Heat moves across the boundary by conduction and turbulent exchange. Water vapor moves upward through evaporation. Momentum is transferred as wind drags across the surface. These exchanges occur continuously, second by second, across the entire ocean. When the surface is warmer than usual over a large area, the cumulative effect becomes significant. The atmosphere above receives more heat and moisture than it would under average conditions, and this can alter pressure and wind patterns over time. Instruments that monitor the ocean skin provide high-resolution data. Satellite sensors can detect small changes in temperature across wide regions. Buoys record temperature at fixed locations, offering time series that show how conditions evolve. These observations are combined into maps that forecasters use to identify the extent and intensity of warming. The persistence of warm anomalies over several months is a key indicator of El Niño strength. Short-lived fluctuations are less important than the sustained pattern that influences seasonal climate. For the United States, the ocean skin in the equatorial Pacific may seem distant, but it plays a role in shaping the atmospheric conditions that later affect weather patterns. The surface warmth acts as an energy source that can modify where and how the atmosphere releases heat through clouds and precipitation. This modification can influence the position and strength of large-scale circulation features, including the paths of storms. The effect is indirect but meaningful, especially when the warming is strong and widespread. The ocean skin is a delicate interface, only a small fraction of the ocean's depth, yet it carries the signal that the atmosphere can feel most directly. During El Niño, it becomes a map of change, showing where the tropical Pacific departs from its usual state. The warmth that spreads across this layer is both a record of past wind changes and a driver of future atmospheric responses. It is a quiet surface, often appearing smooth from above, yet it holds the energy that can influence weather far from its origin. In this fifth region, the focus narrows to the immediate boundary between ocean and air. It is here that measurements are taken, anomalies are defined, and exchanges occur without delay. The ocean's skin is not isolated. It is connected to deeper layers below and to the atmosphere above. But in this view it stands as the visible expression of El Niño at the surface, its temperature, its moisture exchange, and its interaction with clouds form the basis for understanding how a distant ocean can begin to shape conditions across a continent. Beneath the warm surface of the tropical Pacific, the ocean changes with depth. The upper water is usually lighter and warmer, while deeper water is colder and denser. Between these layers lies a transition zone called the thermocline. The thermocline is the depth range where temperature drops quickly from warm surface water to cooler water below. It is not a wall, and it is not perfectly flat. It slopes, rises, sinks, and shifts as winds and currents move the ocean. During El Niño, this hidden boundary changes shape, and its movement helps explain why surface warming can spread and persist across the equatorial Pacific. In normal conditions, the thermocline is deeper in the western tropical Pacific and shallower in the eastern tropical Pacific. This tilt develops because the trade winds push warm surface water westward. Warm water piles up the western basin, and the layer of warm water becomes thicker there, in the east, near the coast of South America. The warm layer is thinner, and cooler water lies closer to the surface. This allows upwelling to bring cooler water upward more easily. The usual slope of the thermocline is therefore one of the main structures holding the tropical Pacific in its ordinary state. When the trade winds weaken during El Niño, the slope of the thermocline relaxes. The western warm layer is no longer held as strongly in place, and the eastern thermocline can sink deeper than usual. When it sinks in the east, cooler water becomes less available to reach the surface. The surface then remains warmer because the upward supply of cold water is reduced. This does not require the deep ocean to become warm. It requires the boundary between warm and cool water to move downward enough that the surface is less connected to the colder layer below. The thermocline also rises in some western areas as the basin adjusts. The ocean is conserving mass and responding to changing winds, so a sinking thermocline in one region can be linked with shallower conditions elsewhere. These changes move through the ocean as broad waves. They are not the waves seen breaking on a beach. They are large internal waves that alter temperature structure and sea level over great distances. Along the equator, these waves can travel efficiently because the rotation effect changes sign across the equator. They help transmit wind changes from one part of the basin to another. One important type of wave in this setting is called a Kelvin wave. A Kelvin wave is a broad oceanic disturbance that can move eastward along the equator, carrying changes in sea level and thermocline depth. When westerly wind bursts occur over the western or central Pacific, they can generate downwelling Kelvin waves. Downwelling means that the thermocline is pushed deeper. As these waves travel eastward, they deepen the thermocline and reduce the upward reach of cold water. This supports warmer surface temperatures in the central and eastern Pacific. The process unfolds over weeks, linking short wind events to broader oceanic change. The thermocline is measured by instruments that record temperature at different depths. Moored buoys in the tropical Pacific collect such data, showing how warm and cool layers move over time. Profiling floats descend and rise through the water, measuring temperature and salinity as they travel. Ships also contribute observations. These measurements reveal that El Niño is not only a surface event, it includes a reorganization of the upper ocean structure. The surface warmth visible to satellites is connected to this deeper boundary, where the ocean's vertical arrangement has changed. The position of the thermocline affects the supply of nutrients as well as temperature. In the eastern tropical Pacific, cooler, deeper waters often contain nutrients that support marine life when they rise toward the surface. When El Niño deepens the thermocline and weakens upwelling, nutrient supply can decline in affected regions. This can influence plankton, fish, seabirds, and larger marine ecosystems. The weather concern for the United States comes through the atmosphere. But the oceanic change is also a biological and chemical change within the Pacific. The thermocline marks the boundary where these changes begin to connect. The thermocline is shaped by density. Warm water is generally less dense than cold water, and fresh water is less dense than salty water. Temperature is usually the dominant factor in the tropical Pacific, but salinity also matters. Rainfall, evaporation, and currents can alter salinity near the surface, changing how easily water mixes vertically. A strong density contrast can keep warm surface water separated from colder water below. During El Niño, changes in rainfall and wind can modify this layering, but the main signal remains the altered depth of the temperature transition. Mixing across the thermocline is limited compared with mixing within the upper layer. Strong winds, currents, and turbulence can move some water across it, but the density contrast resists easy blending. This means that when the thermocline deepens, the surface can be protected from cold water for a time. When it shoals or moves closer to the surface, cold water can more easily influence surface temperature. The depth of this boundary therefore controls how strongly the deeper ocean can cool the surface. In El Niño, the eastern and central Pacific surface is often warmer, because the cold reservoir below becomes less accessible. The thermocline also affects air pressure indirectly. A deeper thermocline in the east helps maintain warm surface water. Warm surface water increases heat and moisture exchange with the air. The atmosphere then becomes more favourable for rising motion in places that are usually less active. The resulting pressure changes can further weaken the trade winds, reinforcing the oceanic changes. The thermocline itself is hidden below the surface, but its movement helps support the visible climate pattern above. Forecast models represent the thermocline because its position influences how El Niño develops and fades. If warm water below the surface is available to support continued surface warming, the event may strengthen or persist. If the subsurface structure begins to cool or shift in a way that brings cold water closer to the surface, the event can weaken. Scientists therefore examine not only surface maps, but also depth sections across the equatorial Pacific. These sections show the warm layer, the cooler layer, and the sloping boundary between them. They provide a view of the event's internal support. At this sixth region, the exploration has moved inward from the ocean skin to the hidden slope beneath it. The thermocline is quiet, broad, and unseen from space, yet it governs how the surface connects with the colder ocean below. During El Niño, its slope relaxes, its eastern side sinks, and its shape becomes part of the larger coupled pattern. Warmth at the surface becomes more durable when cold water is held farther down. The boundary does not create the event alone, but it helps sustain the warm surface that the atmosphere can feel. In this inner ocean layer, the warning begins to rest not only on what is visible, but on the structure beneath the visible sea. Below the surface layer and around the shifting thermocline, the tropical Pacific contains a broad store of heat. This store is not a sealed chamber, and it does not have sharp walls. It is a volume of warm water held within the upper ocean, thicker in some places and thinner in others, shaped by winds, currents, waves, and mixing. During El Niño, the subsurface heat pool becomes important because it helps sustain the warmth that appears at the surface. It is quieter than the winds above and less visible than the surface maps, yet it carries part of the event's strength. The warm water volume of the equatorial Pacific is measured by looking at temperatures below the surface across a wide region. Scientists examine how much water is warmer than a chosen reference level, and they track where that water sits along the basin. In usual conditions, a large share of this warm water is held in the western Pacific, where trade winds keep the warm layer deep. During El Niño, some of this heat shifts eastward. The movement is not a simple flood, but a gradual redistribution through currents and broad ocean waves. As the warm volume spreads, it can support surface temperature anomalies for months. The subsurface heat pool matters because the surface alone can change quickly. A cloudy period, a burst of wind, or a short episode of mixing can cool the ocean skin for a time. If warm water lies beneath, the surface can recover. If colder water lies close below, the surface is more easily cooled. In a strong El Niño, warmth below the surface helps maintain the surface anomaly, even when short weather events disturb it. This makes subsurface observations especially valuable for forecasting, because they show whether the surface warming has support beneath it. Heat in the upper ocean is stored as thermal energy. Water has a high heat capacity, which means it can hold a large amount of energy for a given change in temperature. This property makes the ocean a slow-moving part of the climate system. The atmosphere can change rapidly from day to day, but the ocean responds more gradually and can preserve anomalies over long periods. When a large volume of warm water sits below the surface, it represents a reservoir that can influence the months ahead. It does not guarantee a specific weather outcome, but it strengthens the physical basis for a lasting climate pattern. The heat pool is moved by currents along and near the equator. Some currents flow eastward below the surface, while surface flows often depend strongly on wind. The equatorial undercurrent is one important eastward flow beneath the surface. It carries water from the western and central Pacific toward the east, usually below the top layer. During El Niño, changes in winds and pressure can alter how this current interacts with the warm water volume and the thermocline. The details vary from event to event, but the subsurface circulation remains part of the way heat is redistributed across the basin. The Western Pacific warm pool is often the starting store of much of this heat. It lies under regions where sea surface temperatures are normally high and deep. Atmospheric convection is common. In years leading into El Niño, changes in wind can build or release this stored warmth. When the trade winds weaken, the warm pool can spread eastward through the upper ocean. The warm water does not need to travel as a single body. Instead, the temperature structure changes along the equator, and warm anomalies appear below the surface in the central and eastern basin. These anomalies can later influence the surface if the thermocline remains deep enough, and mixing allows heat to reach upward. Subsurface heat is not visible to ordinary satellite temperature measurements, so it requires direct or indirect observation. Moored buoys measure temperature at several depths. Profiling floats rise and sink through the water, recording vertical temperature profiles. Ocean reanalysis systems combine observations with models to estimate conditions in places where measurements are sparse. These tools reveal whether the upper ocean is gaining heat, losing heat, or shifting heat from west to east. Forecast centers use this information because the subsurface state often gives early clues about the future development of El Niño. The heat pool also interacts with sea level. Warm water expands slightly compared with colder water, and a thicker warm layer can raise the sea surface. Satellite altimeters measure sea surface height, allowing scientists to infer some aspects of subsurface heat content. Higher sea level in the tropical Pacific can indicate a deeper warm layer, although winds, currents, and pressure also affect sea height. During El Niño development, changes in sea level along the equator can show the passage of oceanic waves that carry warm anomalies eastward. These measurements add another view of the hidden reservoir. The redistribution of subsurface heat is tied to balance. When warm water spreads eastward, the western Pacific may lose some heat content. The basin is adjusting to altered winds and pressure. This movement of heat can change rainfall patterns over island regions, affect fisheries near the eastern Pacific, and influence the atmosphere above the Central and Eastern Ocean. Within this section, the focus remains on the inner ocean store itself, where heat is held, how it moves, and how it supports the surface. Its significance lies in persistence. A surface warm anomaly backed by subsurface heat can endure longer than one resting on a shallow warm film. The strength of an El Niño event is partly connected to how much warm water is available below the surface before and during its development. A large subsurface reservoir can support a stronger event if atmospheric coupling also occurs. Coupling means that ocean changes and atmospheric changes reinforce each other. Without coupling, subsurface warmth may not translate into a strong climate signal. With coupling, the warm reservoir helps feed the surface pattern, and the atmosphere responds through altered convection and pressure. This is why forecasters examine ocean heat content together with winds and cloud patterns, rather than treating it as a separate measurement. Uncertainty remains because the subsurface ocean is complex. Small changes in wind bursts, mixing, and wave timing can influence where heat emerges. The same amount of warm water may produce different surface patterns depending on its depth and location. A warm anomaly buried too deep may have limited immediate effect on the atmosphere. A shallower warm anomaly can affect the surface more readily. Forecasts therefore consider the vertical structure of the heat pool. Not only the total amount of heat, the inner ocean has shape as well as quantity. For the United States, the subsurface heat pool is distant and indirect, but it helps explain why an El Niño warning can become more serious when the ocean below the surface is strongly warm. A shallow surface event may fade before it shapes a season. A deeper, well-supported event is more likely to persist long enough to influence winter circulation. The link still passes through the atmosphere and remains probabilistic. But the heat reservoir gives the tropical Pacific a kind of memory. It allows the pattern to continue after short weather changes pass. In this seventh region, the exploration rests within the upper ocean's hidden warmth. The subsurface heat pool is calm in appearance, measured by instruments rather than seen by eyes, and held in layers that shift with currents and waves. It is not dramatic in itself. It is simply water, warmer than usual in the places where it matters, carrying energy through depth and distance. During a strong El Niño, this inner store helps maintain the surface warmth that feeds the atmosphere. The warning therefore reaches inward, from the visible ocean skin to the quiet reservoir beneath, where the event gains endurance. Above the warm tropical Pacific, air begins to rise where heat and moisture gather near the surface. This rising motion is called convection. In weather and climate, convection means the upward movement of warm, moist air that can form clouds and rain when the air cools with height. During El Niño, the main region of tropical convection often shifts away from its usual western focus and becomes more active across the central or eastern equatorial Pacific. This change is one of the clearest ways the ocean's hidden and surface warmth enters the atmosphere. The process begins close to the ocean surface. Warm water heats the air directly above it and increases evaporation. The air becomes warmer and more humid. Humid air contains water vapor, which is an invisible gas. When the air rises, it expands because pressure decreases with height. Expansion cools the air. cooler air cannot hold as much water vapor, so some of the vapor condenses into tiny droplets or ice particles. Clouds form from this condensation. The act of condensation releases latent heat, which is stored energy that becomes available as water changes from vapor to liquid or ice. This heat release helps the air continue rising. In the tropical Pacific, convection is not only a local cloud process, it shapes large-scale pressure and wind patterns. Where air rises persistently, surface pressure tends to be lower. Air flows toward that region near the surface, and air spreads outward higher above. In normal conditions, the strongest tropical convection is often located over the warm western Pacific. During El Niño, warmer waters across the central and eastern Pacific can support more rising air there. This shift changes the distribution of tropical heating in the atmosphere. The atmosphere does not respond only to the temperature of the water, but to where heat is released inside tall clouds. Cloud towers in the tropics can reach high into the troposphere. They are built from air that rises through many layers, condensing water vapor and releasing heat along the way. Around them, other air may sink, warming and drying as it descends. Large convective regions therefore create a pattern of rising and sinking motion. During El Niño, when convection moves eastward, the surrounding pattern also moves. Rainfall increases in some oceanic regions and decreases in others. This redistribution affects tropical islands, marine ecosystems, and the broader circulation above the Pacific. The rising moist air is organized in clusters, bands, and broad cloudy zones rather than as one continuous wall. Some days bring stronger thunderstorm activity, other days are quieter, over weeks and months. The average location of this activity reveals the climate signal. Forecasters look at rainfall estimates, outgoing radiation from cloud tops, and wind patterns to identify where convection is strongest. Outgoing radiation is the heat energy emitted from Earth and the atmosphere into space. Tall, cold cloud tops emit less of this radiation, so satellite measurements can help locate deep tropical cloud regions. In El Niño conditions, the eastward shift of convection affects the Walker circulation. The Walker circulation is the broad east-west overturning flow along the equatorial Pacific. When rising air becomes stronger farther east, the usual pattern weakens or reorganizes. This can further reduce the trade winds at the surface, which supports continued ocean warming. The connection is a loop between ocean and atmosphere. Warm water supports rising moist air. Rising moist air changes pressure and winds. Change winds help maintain or expand the warm water. This loop is central to the strength of a mature El Niño event. The rising air also influences rainfall patterns near the tropics. Places that normally receive frequent tropical rainfall may become drier if the main convective zone shifts away. Places that are usually less rainy may receive more clouds and precipitation. These changes are not uniform, because local geography, seasonal winds, and surrounding ocean temperatures shape each region. Still, the broad movement of convection across the Pacific is one of the main signatures of El Niño. It shows that the atmosphere has accepted the ocean's surface warmth as an active heat source. The height of the rising air matters. Shallow clouds release heat lower in the atmosphere and have a limited effect on global circulation. Deep convection releases heat through a much greater depth, reaching into the middle and upper troposphere. This deeper heating is more effective at generating large atmospheric waves that can extend into the subtropics and mid-latitudes. The release of heat high in the tropics changes pressure surfaces aloft and can influence winds far from the original cloud systems. In this section, the focus remains on the rising moist air itself, where the ocean's warmth is converted into vertical motion and cloud heat. Moisture is essential to this process. Without enough water vapor, Rising air may cool and stop before forming deep clouds. Warm tropical oceans provide abundant moisture, but atmospheric stability also matters. Stability describes whether air resists or supports vertical motion. If the atmosphere is too stable, warm, moist air may remain trapped near the surface. During El Niño, the distribution of warmth and convergence can reduce stability in key regions, encouraging deep cloud growth. Convergence near the surface brings air together, forcing some of it upward. When convergence occurs over warm water, deep convection becomes more likely. The release of latent heat is sometimes described as a fuel for tropical weather, but it is more precise to see it as an energy transfer within the climate system. The ocean has stored heat from sunlight. Evaporation moves some of that energy into water vapor. Condensation releases it within clouds. The atmosphere then carries the effect through winds and pressure changes. This chain allows the ocean surface to influence air far above it. During a strong El Niño, the chain becomes organized over a large region, making the tropical heating anomaly strong enough to affect seasonal patterns. Measurements of convection include satellite images, rainfall products, cloud-top temperatures, and wind observations. Scientists compare these data with sea surface temperature to see whether the warm ocean is producing the expected atmospheric response. If warm water exists without a strong convective shift, the event may have weaker remote effects. If deep convection moves clearly into the central and eastern Pacific, the atmospheric bridge becomes stronger. This is why forecasters do not rely only on ocean temperature. They watch the clouds and rising air as evidence that the climate system is coupled. For the United States, rising moist air over the tropical Pacific is not the direct weather that reaches the ground. It is the source of upper-level heating that can reshape larger wind patterns. The clouds themselves remain far away, but their heat release changes the atmosphere's balance. The influence moves outward through wave patterns and circulation adjustments. The link is indirect, yet it is physically grounded. Warm tropical water changes convection. Convection changes atmospheric heating, and atmospheric heating changes the flow that guides storms. In this 8th region, the exploration moves from the ocean into the vertical body of moist tropical air. The scene is no longer only water storing heat, it is air lifting from the surface, cooling with height, forming clouds, and releasing energy. The motion is steady in the average, even though individual clouds grow and fade. During El Niño, the place where this rising air is most persistent can shift across the Pacific, marking a major step in the transfer of ocean warmth into atmospheric circulation. The warning gains height here, rising from the sea into the clouds, where moisture and heat become the language of the wider climate system. High above the tropical Pacific, the heat released by rising moist air spreads into broader wind paths. These paths lie mainly in the middle and upper troposphere, where pressure surfaces slope and air moves in wide currents around the planet. During El Niño, the shifted zone of tropical heating can alter these upper air patterns. The change does not appear as a single stream of air moving directly from the equator to the United States. It appears as a set of atmospheric waves and pressure changes that connect distant regions through the structure of the moving air. The upper troposphere is a region of thinner air, colder temperatures, and stronger winds than the lower atmosphere. It is still part of the weather-making layer, but its motions are broader and often faster. When deep tropical clouds release latent heat high in the atmosphere, the air column warms and expands. This expansion changes the height of pressure surfaces. Air responds by moving along gradients, and because Earth rotates, the flow curves into large patterns. These upper-level changes can extend away from the tropics into the subtropics and mid-latitudes, where they interact with existing wind belts. One important way tropical heating affects distant regions is through planetary waves. These are large bends in the atmospheric flow that can span thousands of kilometers. They're sometimes called Rossby waves, after the scientist who helped describe them. A Rossby wave is a broad meander in the wind field caused by Earth's rotation and the change in that rotation effect with latitude. When tropical heating shifts during El Niño, it can disturb the upper atmosphere in a way that generates or alters these waves. The waves then shape areas of high and low pressure far from the original heat source. The connection from the tropical Pacific to North America is often called a teleconnection. A teleconnection is a relationship between climate patterns in distant places. It does not mean that one storm travels the entire distance. It means that a persistent change in one region affects the probability of certain circulation patterns elsewhere. In El Niño, the tropical heat source can encourage a wave train over the Pacific and North America. A wave train is a sequence of linked high and low pressure regions in the upper atmosphere. Its exact shape varies from event to event, but it can influence where storm tracks strengthen or shift. The high-level wind paths are important because they steer weather systems. Near the surface, storms move along boundaries between air masses and respond to local pressure patterns. Higher up, the broader flow helps guide their direction and speed. When the upper air pattern changes, storms may follow different routes than they would in a neutral year. Some regions may receive more frequent systems, others may experience fewer. The influence remains probabilistic because storms also depend on shorter-term conditions, but the upper winds help set the background. During strong El Niño events, the upper-level response can be more pronounced because the tropical heating anomaly is stronger and more persistent. The word anomaly here means a departure from the usual state. If deep convection remains shifted into the central or eastern Pacific for weeks or months, the atmosphere has a sustained source of altered heating. This can maintain wave patterns that affect the North Pacific and North America through the cool season. Yet the atmosphere is not a machine that repeats the same output each time. The location of tropical heating, the state of other oceans, the polar circulation, and random weather variability all influence the final pattern. The high-level wind paths also interact with the subtropical jet stream, a band of strong winds that forms near the boundary between tropical and mid-latitude air. A jet stream is a narrow region of fast-moving air in the upper troposphere. During El Niño, enhanced tropical heating can strengthen or shift parts of the subtropical jet over the Pacific. This jet becomes a pathway along which storms can develop and travel. At this stage, the focus remains on the upper air connection rather than on the storms themselves. The key point is that heat released in tropical clouds changes pressure and wind patterns at altitude. The structure of the upper atmosphere is measured by satellites, weather balloons, aircraft, and numerical weather models. Weather balloons carry instruments upward and record temperature, pressure, humidity, and wind. Satellites track water vapor and cloud motion, while aircraft provide wind and temperature observations along flight paths. Models combine these observations to describe the full three-dimensional state of the atmosphere. Forecasters use this information to see whether the expected El Niño-related upper patterns are forming. A strong ocean signal becomes more relevant to United States weather when the upper air pathways align. The upper air response can influence temperature as well as precipitation. Broad ridges, which are northward bulges of higher pressure aloft, can favor warmer and drier conditions beneath them. Broad troughs, which are southward dips of lower pressure aloft, can favor cooler air, clouds, and storm development. El Niño can alter where these ridges and troughs tend to appear. The result is not one simple national pattern. It is a shifting distribution of odds. where some regions become more likely to experience wet periods, mild conditions, or active storm tracks during parts of the season. Energy moves through these upper air patterns without needing the air itself to travel all the way from the tropics to the mid-latitudes. This distinction is important. The atmosphere transmits influence through waves, just as a disturbance can pass through water without the same water moving across the whole basin. In the upper troposphere, pressure and wind anomalies can propagate through the background flow. The existing state of that flow affects how the signal travels. If the background winds are favourable, the tropical disturbance can project more strongly into the North Pacific and North America. If they are less favourable, the response may be weaker or displaced. Uncertainty in this region comes from the complex structure of the atmosphere. The same tropical heating anomaly can lead to different outcomes depending on the timing of weather systems already present. Other climate patterns can add their own influence. The Arctic, the North Pacific, the Atlantic, and land snow cover can all affect circulation during a season. El Niño is a major source of predictability, especially for winter patterns, but it is not the only source. Forecasts therefore describe likelihoods and ranges rather than fixed results. For the United States, the high-level wind paths are the atmospheric bridge between the tropical Pacific and regional weather. They do not determine every storm, but they shape the large currents in which storms form and move. A shifted tropical heat source can set up waves that favour a more active southern storm path. Changes in the North Pacific flow and altered temperature patterns across parts of the country. These are broad tendencies, not local guarantees. The precision increases only when shorter-term weather forecasts become available. In this 9th region, the exploration has reached the upper air pathways above the tropical heating source. The ocean has warmed, moist air has risen, and heat has been released in deep clouds. Now that heat appears as altered pressure surfaces, broad waves, and stronger or shifted winds aloft. The atmosphere carries the signal outward through structure rather than through a straight road. The high-level wind paths are wide, invisible corridors of motion, linking the tropics with distant latitudes. In their slow, seasonal adjustment, the El Niño warning begins to approach the continent through the upper sky. Over the North Pacific, the upper winds gather into a stronger and more focused current known as the Pacific jet stream. This jet stream is a fast-moving band of air in the upper troposphere, shaped by temperature differences between tropical and higher latitude air and by Earth's rotation. It does not stay in one place. It shifts north and south, strengthens and weakens, and develops bends that guide storms across the ocean. During El Niño, the changes that begin with tropical heating can influence this high wind corridor, making it an important region between the equatorial Pacific and the United States. The Pacific jet stream forms where strong temperature contrast creates steep pressure gradients aloft. A pressure gradient is a change in pressure over distance, and air accelerates where that change is strong. In the upper atmosphere, the flow becomes concentrated into narrow ribbons of high wind. These ribbons can extend across much of the Pacific, especially during the cooler months when temperature contrasts are sharper. The jet stream is not a solid boundary, but it often acts like a pathway. Storm systems tend to grow along it, draw energy from it, and move within its broader flow. In an El Niño year, the subtropical branch of the Pacific jet often becomes more active or extends farther eastward. This is linked to enhanced tropical convection and upper-level heating over the central and eastern Pacific. The added heating can alter the upper pressure field and strengthen westerly winds across parts of the basin. Westerly winds blow from west to east. When these winds are stronger and more continuous, storms can have a clearer route across the Pacific toward North America. This does not mean every storm becomes severe, but it can increase the chance of a more active storm track in some areas. The jet stream contains both smooth flow and sharp disturbances. Some sections are nearly straight, carrying air rapidly across long distances. Other sections bend into troughs and ridges. A trough is a dip in the upper-level flow that can support rising motion and storm development. A ridge is a bulge that often supports sinking air and calmer weather. During El Niño, the balance between these features can change over the North Pacific. The jet may become stronger across the southern part of the basin, while the northern track may shift or weaken. The exact pattern depends on the placement of tropical heating and the background state of the atmosphere. Storms draw energy from temperature contrasts and from the upper winds. Over the North Pacific, cold air from higher latitudes can meet milder, moist air from lower latitudes. When the jet stream is strong, it can enhance the growth of low-pressure systems by creating regions aloft where air spreads apart. This spreading air above encourages air below to rise, lowering surface pressure and deepening storms. In an El Niño winter, an extended Pacific jet can provide more opportunities for such storm development across the ocean. Some of these systems may later approach the west coast, while others curve away or weaken before landfall. The jet stream also influences atmospheric rivers. An atmospheric river is a long, narrow corridor of concentrated water vapor transported by winds. Over the Pacific, these corridors can carry moisture toward western North America. They're not caused only by El Niño, and they occur in many climate states. However, when the Pacific jet is strong and directed toward the coast, it can help steer moisture-rich systems into land. The impacts depend on the exact landfall location, duration, terrain, snow levels, and previous ground conditions. At this stage, the focus remains on the oceanic wind corridor that can guide these moisture pathways. The North Pacific is a wide region with its own variability. The Aleutian Low, a semi-persistent low-pressure area near the northern Pacific, often strengthens during winter and influences storm paths. El Niño can affect its position and strength, but other patterns also matter. Sea surface temperatures in the North Pacific, Arctic air outbreaks, and internal atmospheric variability can all change the final structure. The jet stream responds to this full environment. It is influenced by the tropical signal, yet it is not controlled by that signal alone. Forecasters monitor the Pacific jet through wind analyses, satellite water vapor imagery, aircraft observations, and weather models. In satellite images, the jet often appears indirectly through bands of clouds and moisture, with storm systems embedded along the flow. Models show wind speed and direction at upper levels, helping forecasters identify whether the jet is extended, split, or strongly curved. During an El Niño event, these observations reveal whether the expected eastward extension over the Pacific is present. A clear extension can support a more active pattern for regions downstream. The jet stream also shapes temperature patterns. When the flow carries air from the Pacific into North America, it can moderate cold in some regions. When it dips southward, it can allow cooler air to reach lower latitudes. When it remains farther north, southern areas may receive fewer storms. El Niño often changes the distribution of these possibilities during winter, but the details remain variable. A strong jet can bring repeated systems, yet gaps between storms can still occur. Seasonal forecasts describe tendencies over months, while daily weather follows the shorter rhythm of individual disturbances. The position of the jet relative to the coastline matters greatly. A jet aimed toward California can support a different pattern than one aimed toward the Pacific Northwest, or one that splits before reaching land. A split jet occurs when the upper flow separates into northern and southern branches. The southern branch may carry storms across the southern tier of the United States, while the northern branch follows a different path. El Niño can favor a stronger southern branch, but the actual arrangement shifts through the season. The jet stream is therefore a guide, not a fixed road. The Pacific jet also interacts with mountains once storms approach land, but within this region the concern remains over the ocean. Over open water, storms can deepen, moisture can gather, and winds aloft can organize the path. The ocean provides heat and moisture, while the upper winds provide direction and structure. A strong El Niño can increase the likelihood that this over-ocean machinery becomes more active along certain routes. Still, each storm must form under its own immediate conditions. The climate signal changes the background, not every event. For the United States, the Pacific jet is the last broad atmospheric corridor before regional impacts begin. It translates remote tropical heating into a storm track pattern over the ocean. When it strengthens and extends eastward, it can raise the chance of wet and unsettled conditions along parts of the west and south, especially during the cool season. The strongest effects are not uniform, and they depend on timing and landfall. Forecast confidence is usually higher for broad seasonal tendencies than for exact local totals far in advance. In this 10th region, the exploration rests in the fast upper winds over the North Pacific. The Pacific jet stream is invisible except through its effects on clouds, storms, and moisture. Yet it is one of the main pathways by which El Niño influence approaches the continent. It gathers the atmosphere into a long eastward current, shaped by tropical heating, temperature contrasts, and planetary rotation. In its bends and pulses, the distant warming of the equatorial Pacific becomes a pattern of movement over the ocean, carrying the warning closer to the western edge of North America. Along the western edge of the United States, the Pacific Ocean meets mountains, valleys, cities, forests, rivers, and coastlines. This is the first land region reached by many storm systems that cross the ocean from west to east. In an El Niño year, especially one with a strong tropical signal, the western states become an important area of attention because the Pacific jet stream can guide storms toward the coast more often or with different paths than usual. The effects are not the same from Washington to California, and they are not the same from the beaches to the inland mountains. The land receives the atmosphere in uneven ways. The western United States has strong physical contrasts. Coastal areas sit beside the ocean, where marine air can bring clouds, wind, rain, and high surf. Just inland, mountain ranges lift incoming air. Farther east, valleys and basins may lie in rain shadows, where air has already lost much of its moisture. A rain shadow forms when mountains force moist air upward, causing precipitation on one side, while drier air descends on the other side. Because of these contrasts, one storm can bring heavy rain to a coast, deep snow to a high range, and much lighter precipitation to an interior valley. During El Niño winters, parts of California and the southern tier of the West often have increased chances of wetter conditions, though the pattern varies between events. The key pathway is the storm track over the Pacific. When the jet stream carries storms toward the coast at lower latitudes, the West can receive repeated rounds of rain and mountain snow. These storms may arrive with strong winds, low pressure, and long moisture plumes. The impact depends on their timing, their temperature, and how directly they strike the coastline. A season can be wetter than average through several moderate storms, or through fewer but more intense events. Coastal rain is one of the most visible concerns. When moist Pacific air moves inland, it cools as it rises over terrain. Cooling allows water vapor to condense into cloud droplets, and precipitation begins. Along coastal mountains, this lifting can greatly increase rainfall. If soils are already wet, additional rain runs off more easily into streams and rivers. Urban surfaces such as roads and rooftops also increase runoff because they do not absorb water like soil. Flood risk therefore depends not only on the storm, but also on the condition of the ground and the shape of the watershed. Mountain snow is another important part of the Western response. Snowpack acts as a natural reservoir, storing water through the cold season and releasing it as temperatures rise. In El Niño years, the location and elevation of snowfall can vary widely. A storm that is cold enough can build snowpack in the Sierra Nevada, the Cascades, the Rockies, and other ranges. A warmer storm can raise snow levels, causing rain to fall where snow would normally accumulate. Snow level means the elevation above which precipitation falls mainly as snow. When snow levels are high, mountain runoff can increase quickly, especially if rain falls on existing snow. Flooding in the west often depends on both precipitation intensity and landscape condition. Steep terrain can move water rapidly downslope. Burned scars from wildfires can increase danger because burned soils may repel water and lack vegetation that would normally slow runoff. In these places, heavy rain can trigger debris flows, which are fast-moving mixtures of water, mud, rocks, and burned material. El Niño does not create the burn scar, but a wetter storm pattern can increase the chance that vulnerable slopes receive intense rainfall. The hazard is local, even though the climate driver is broad. The coast also faces ocean-related effects. Strong Pacific storms can produce large waves, coastal erosion, and periods of high water when storm surge, high tides, and large waves occur together. Low-lying coastal areas can be affected. El Niño can also raise sea levels temporarily along parts of the eastern Pacific by changing winds and ocean temperature structure. Warmer water expands, and changes in currents can alter coastal sea height. These changes are usually measured in small amounts compared with the height of the waves, but they can add to coastal impacts during storms and high tides. The western United States also includes dry regions where precipitation is highly variable. In deserts and semi-arid basins, even a modest increase in seasonal rainfall can be significant. Dry washes can carry sudden flows when storms pass. Soil crusts and sparse vegetation can lead to rapid runoff. Yet not every El Niño brings uniform wetness to every western desert. The position of the jet stream and storm centers controls where rainfall concentrates. Some areas may receive repeated storms, while others remain near average or even dry. Reservoirs and water systems respond to the sequence of storms rather than to the climate label alone. A wet El Niño can help replenish water storage after dry periods, but too much rain in a short time can create flood management challenges. Reservoir operators must consider current storage, expected inflow, snowpack, downstream flood risk, and water supply needs. The balance is complex because forecasts become less precise farther into the future. A strong seasonal signal can suggest increased odds of wet conditions, while individual storm forecasts guide immediate decisions. The West's ecosystems respond as well. Grasslands may green after rain, rivers may carry more sediment, coastal waters may change in temperature and nutrient supply. Forests may benefit from moisture in some areas, while facing damage from wind, saturated soils, or landslides in others. The response is not simply good or bad, it depends on timing, intensity, and the condition of each landscape. A slow, steady series of storms can soak soils and build snowpack. A sudden intense storm over fragile ground can cause damage. In cities, the western impact becomes practical. Storm drains carry runoff from streets. Hillside neighborhoods depend on slope stability. Transportation routes through mountain passes depend on snow, ice, and visibility. Power lines and trees are affected by wind and saturated ground. Emergency planning often focuses on the specific hazards that accompany a wet pattern flooding: mudslides, high surf, and travel disruption. These are local expressions of a broad climate influence. Filtered through infrastructure and terrain, scientific caution remains important. El Niño increases the likelihood of certain Western patterns, especially during winter, but it does not guarantee a single outcome. Historical strong events have brought major storms to parts of the West, yet differences in ocean warming location and atmospheric circulation have produced different regional results. The western United States is therefore a region of heightened attention, rather than a place with a fixed destiny. Forecasts improve as the season unfolds and as individual storms appear within shorter-range prediction windows. In this 11th region, the climate signal reaches the continent's western edge. The Pacific jet stream, shaped by tropical heating and upper air waves, guides storms toward land, where mountains lift moist air and coastlines receive wind and waves. The broad warning becomes rain on hillsides, snow in high ranges, runoff in rivers, and surf along the shore. The western United States shows how El Niño influence must pass through geography before it becomes impact. The land is not a passive surface. It shapes the storm, divides the moisture, stores the snow, and turns a distant ocean pattern into regional weather. Across the southern United States, the El Niño signal often becomes clearer during the cool season, when storm paths can shift across the lower part of the country. This region extends from the deserts and borderlands of the Southwest through Texas, the Gulf Coast, the lower Mississippi Valley, and toward the southeast. It is a wide and varied belt, with mountains, plains, wetlands, rivers, farms, ports, and cities. During a strong El Niño, the southern tier often has an increased chance of wetter conditions, especially when the Pacific jet stream supports frequent storm systems moving from west to east. The southern United States is strongly influenced by moisture. To the west, storms can enter from the Pacific and cross the southwest. To the south, the Gulf of Mexico can supply warm, humid air. When upper-level disturbances move over this region and moisture is available, clouds and precipitation can develop across long distances. El Niño can make this setup more common by supporting a stronger southern branch of the jet stream. This does not create constant rain, and it does not make every storm severe. It changes the background odds, making active periods more likely in many parts of the southern belt. In the southwest, the response depends on how storms cross dry landscapes and mountain terrain. Rain can replenish soils and reservoirs, but heavy precipitation can also cause flash flooding in arroyos, canyons, and desert washes. An arroyo is a dry channel that can fill quickly during intense rain. Dry ground may absorb some water at first, but intense rainfall can exceed the soil's ability to take it in. In steep or rocky terrain, water moves rapidly downhill. The effect can be sudden. Even when the larger seasonal pattern develops slowly, Texas often sits near the meeting place of Pacific storm energy, Gulf moisture, and continental air masses. During El Niño winters, parts of Texas and the southern plains can lean wetter and cooler than average, though the pattern varies with storm track and air mass placement. When moist air from the Gulf moves inland and is lifted by a front or upper-level disturbance, widespread rain can occur. If colder air is present, winter precipitation may develop in some areas, though exact outcomes depend on near-surface temperatures and the depth of cold air. Seasonal forecasts cannot determine these local details far in advance. Along the Gulf Coast, the southern signal is often tied to repeated storm systems and frontal boundaries. The Gulf of Mexico provides moisture, while upper-level winds can support lifting and storm organization. Rainfall can become heavy when storms move slowly or when several systems pass over the same area. Low-lying coastal plains are sensitive to drainage issues, especially where urban development has replaced wetlands or natural soils. Rivers may rise after repeated rainfall over their basins. The timing between storms becomes important because the ground needs time to drain and streams need time to recede. The lower Mississippi Valley is another area where rainfall can accumulate over large watersheds. Rivers integrate precipitation from broad regions, so flooding can result from repeated storms far upstream as well as local rain. In an El Niño pattern, a more active southern storm track can increase the chance of wet periods, but river response depends on antecedent conditions. Antecedent conditions are the conditions already present before a new event begins: wet soils, high reservoir levels. And elevated river stages can increase flood risk when new rain arrives. Dry soils and low rivers may absorb or store more water at first. The southeast includes forests, coastal plains, Piedmont regions, and major river systems. During many El Niño winters, parts of the southeast have increased odds of above-average precipitation and cooler than average conditions, especially when the southern jet is active. Cooler in this context means relative to the region's average, not necessarily severe cold. Cloud cover and rain can limit daytime warming. Frequent storms can bring periods of unsettled weather. Yet warm spells can still occur between systems, and the full season may contain both wet and quiet intervals. Storm severity in the southern United States is influenced by more than El Niño. Severe thunderstorms require moisture, instability, wind shear, and a lifting mechanism. Instability means air near the surface can rise strongly if lifted, while wind shear means changes in wind speed or direction with height. El Niño can affect the background storm track and temperature pattern, but it does not determine every severe weather outbreak. In some regions and seasons, altered circulation can change severe weather probabilities, but individual events require short-term forecasting. This distinction keeps the seasonal signal separate from daily hazards. Agriculture across the southern belt can be affected by shifts in rainfall and temperature. Winter wheat, pasture, citrus, vegetables, and other crops respond to soil moisture. Cold snaps, cloudiness, and disease pressure. Wet conditions can help drought-stressed areas recover, but excess rain can delay fieldwork, increase erosion, and affect plant health. Cooler, cloudier periods can slow growth in some crops. The outcome depends on crop type, planting schedule, drainage, and the timing of weather events. El Niño provides a seasonal tendency, while farmers experience the pattern as a sequence of workable and difficult days. Water supply can benefit from wetter conditions in some southern basins. Reservoirs may refill, aquifers may receive recharge where geology allows, and drought categories may improve. At the same time, too much rainfall can overwhelm drainage systems. The difference between beneficial rain and damaging rain often lies in intensity and timing. A moderate series of storms spread over weeks can reduce drought. A short period of very heavy rain can cause flooding while leaving deeper drought concerns only partly resolved. The climate pattern sets the stage, but the hydrologic response is shaped by pace. Coastal areas of the south also face interactions between storms, tides, and sea level. Winter storms can bring strong winds, rough surf, and heavy rain even outside the tropical cyclone season. El Niño is often associated with reduced Atlantic hurricane activity during summer and autumn because of increased wind shear over parts of the tropical Atlantic. But the present focus remains the cool season southern United States and its storm track along the Gulf and Atlantic coasts. Drainage can be slowed when high tides or onshore winds keep water from flowing easily into bays and estuaries. This can worsen flooding during heavy rainfall. Public infrastructure across the southern states must manage water in both scarcity and excess. Roads, culverts, levees, storm drains, reservoirs, and wastewater systems all respond to precipitation patterns. In a wetter El Niño winter, weaknesses in these systems may become more visible. Rural areas may face washed-out roads or saturated fields. Urban areas may experience street flooding and transportation delays. Coastal cities may need to consider tide timing during storm events. These impacts are not caused by the climate pattern alone, but by the meeting of climate, weather, land, and human design. The southern United States is often described as one of the regions with stronger El Niño influence, but the signal still varies from one event to another. The location of a warm water in the Pacific, the strength of the jet stream, the state of the Gulf, and the behavior of other atmospheric patterns all shape the outcome. A strong El Niño raises attention because the tropical forcing is larger, yet it does not remove uncertainty. Forecasts remain most useful when they describe elevated risk, likely tendencies, and the need to monitor shorter-range predictions as storms form. In this 12th region, the El Niño influence moves across the lower part of the country, where Pacific storm energy and Gulf moisture can meet. The broad pattern becomes rain in dry channels, clouds over winter fields, rising rivers, and long bands of precipitation along the coast. It can bring relief to drought in some places and flooding concern in others. The southern United States shows how a shifted tropical ocean can guide the atmosphere into a more active path, while local moisture, terrain, and drainage decide how the path is felt on the ground. Across the central United States, the influence of El Niño becomes less direct and more dependent on the meeting of surrounding air masses. This region includes the Great Plains, the central lowlands, the interior river basins, and large agricultural landscapes that stretch between the Rocky Mountains and the Mississippi Valley. It lies away from the oceanic source of the pattern and away from the first coastal landfall zones. Here, El Niño often appears as a shift in seasonal probabilities rather than a clear and uniform signal. Soil moisture, storm tracks, snow cover, and temperature swings all shape how the pattern is experienced. The central United States is open to air from many directions. Cold air can move southward from Canada. Warm and humid air can move northward from the Gulf of Mexico. Dry air can descend from the Rockies or spread from the southwest. Pacific air can cross the mountains and enter the plains in modified form. Because the region lacks a major east-west mountain barrier within its interior, air masses can travel long distances. Weather can change quickly when these air masses meet. El Niño can alter the larger circulation that guides these movements, but the local result depends on timing and placement. During many El Niño winters, parts of the northern central United States have increased chances of milder conditions, while parts of the southern central region may lean wetter or cooler. These tendencies are averages drawn from past events, not fixed outcomes. The central region often sits near transition zones between wetter and drier patterns, or between mild and cold air. A small shift in storm track can move the main precipitation area hundreds of kilometers. This makes the region sensitive to details that seasonal forecasts cannot fully resolve. Soil moisture is one of the main inner conditions in this region. It reflects past rainfall, evaporation, plant use, snowmelt, and drainage. Wet soil changes how the land exchanges heat with the atmosphere. More energy goes into evaporating water, which can limit daytime heating. Dry soil warms more quickly and can support hotter conditions in warm seasons. During an El Niño-influenced cool season, changes in precipitation can alter soil moisture before spring planting. Wet soils may delay fieldwork, while improved moisture can help areas recovering from drought. Agriculture makes the central United States especially sensitive to seasonal climate shifts. Winter wheat, corn, soybeans, sorghum, pasture, and livestock systems all depend on precipitation timing and temperature. A wetter southern storm track can help replenish moisture in parts of the plains, but excess rain can lead to muddy fields, erosion, and planting delays. Milder winter conditions can reduce heating demand and limit some cold stress on livestock, but they can also affect pests and freeze-thaw cycles. The outcome is not a single benefit or harm. It is a balance shaped by local soils, crops, and weather sequences. Snow cover is another important part of the central response. Snow reflects sunlight, insulates the ground, stores water, and affects near-surface temperatures. In a milder El Niño winter, some northern central areas may experience less persistent snow cover, though individual storms can still bring heavy snow. Farther south, snow may be less common, but when cold air is in place and moisture arrives, winter storms can still occur. The exact line between rain, freezing rain, sleet, and snow depends on temperature layers near the ground and above it. Seasonal climate patterns cannot determine these details far ahead. The central United States also contains major river systems. The Missouri, Arkansas, Red, Platte, and Mississippi tributaries collect water from wide areas. River response depends on precipitation over the basin, soil saturation, snowpack, and the timing of thaw. A wetter pattern in parts of the region can raise flood concern if storms repeat or if snowmelt adds to runoff. In other areas, moderate precipitation can improve drought conditions and support water supply. The same climate pattern can therefore ease one hazard while increasing another, depending on location and timing. Storm development over the central plains often depends on contrasts. Warm, moist air from the south may meet colder, drier air from the north or west. Upper-level disturbances can provide lift, and wind shear can organize storms. El Niño can influence the frequency and path of these disturbances, but severe weather remains controlled by short-term ingredients. In winter and early spring, the central region can experience rain, snow, ice, or thunderstorms depending on the air mass structure. The climate signal changes the background, while daily weather decides the form. Drought is a recurring concern in the central United States. El Niño can sometimes bring improved moisture to parts of the southern plains, but the central and northern plains may have weaker or more variable relationships. Drought recovery requires precipitation that is sustained enough to recharge soils, streams, and groundwater. A single wet month may help surface conditions but may not fully restore deeper deficits. Conversely, a dry stretch during an El Niño year can still occur if the storm track stays away. This is why drought outlooks combine climate signals with existing moisture conditions and shorter-term forecasts. Temperature patterns across the central region are shaped by clouds, snow cover, wind direction, and the larger flow aloft. El Niño can tilt the odds toward milder conditions in some northern areas because the jet stream pattern may reduce the frequency or intensity of Arctic air outbreaks. Yet cold outbreaks can still happen. The polar air reservoir remains present, and weather systems can still draw it southward. A seasonal average may be mild even if it contains several sharp cold episodes. This distinction matters for energy demand, livestock care, transportation, and crops. Wind is also a regular feature of the central United States. Strong pressure differences can produce broad wind events across the plains. These winds affect travel, wildfire behavior in dry grasslands, soil erosion, and evaporation. El Niño's influence on wind is less simple than its influence on some precipitation patterns, but changes in storm tracks and pressure systems can alter windy periods. In dry areas, even a cooler season can carry fire risk if vegetation is cured, humidity is low, and winds are strong. Wet periods can reduce that risk temporarily, but later growth can become fuel when it dries. The central region shows why El Niño impacts are often described through probability. It lies between stronger signals to the south and other influences from the north and west. A strong El Niño can shift the odds, but the region's weather remains a blend of competing air masses and storm paths. Forecasts may identify elevated chances of certain seasonal conditions, yet local planning still depends on monitoring individual systems. Farmers, water managers, transportation agencies, and emergency planners all work with this layered uncertainty. In this 13th region, the climate signal moves inward across open plains and river basins. The influence is quieter than at the coast and less uniform than along the southern storm track. It appears in soil moisture, snow cover, planting conditions, river response, and the balance between mild air and cold intrusions. The central United States receives El Niño as a set of altered probabilities passing through a landscape that is already sensitive to timing. The distant tropical Pacific does not decide every outcome here. It adjusts the large pattern, while the interior land and its changing air masses give that pattern its final form. Across the eastern United States, the El Niño signal reaches a region shaped by the Atlantic Ocean, the Appalachian Mountains, the Great Lakes, broad river valleys, coastal plains, and dense population centers. This region lies far from the tropical Pacific source, but it remains connected through the upper air patterns that guide storms across the continent. By the time the influence reaches the east, it has passed through ocean warming, tropical convection, upper-level waves, the Pacific jet stream, western terrain, southern moisture paths, and central air mass boundaries. Here, the pattern becomes a final continental expression, filtered through local geography and nearby waters. The eastern United States is not one climate zone. New England has cold winters, coastal storms, and complex terrain. The mid-Atlantic sits between northern cold air and southern moisture. The southeast has warmer conditions, coastal plains, forests, and access to Atlantic and Gulf moisture. The Great Lakes region has its own lake effects, especially when cold air crosses relatively warmer water. Because of this variety, El Niño does not produce one simple eastern outcome. It shifts the odds of certain patterns, while the actual weather depends on storm paths, temperatures, and moisture sources. During many El Niño winters, parts of the southeast and mid-Atlantic have increased chances of wetter conditions, while parts of the northern tier may lean milder. These tendencies arise when the southern storm track is more active, and when cold air intrusions are less persistent in some northern regions. However, the boundary between rain and snow can be sensitive. A storm moving along the east coast can bring heavy rain to one area, snow to another, and mixed precipitation in between. A small shift in track can change impacts sharply. Seasonal forecasts can suggest the background pattern, but storm-scale forecasts determine details. The Atlantic Ocean plays an important role in this region. Coastal storms can draw moisture from the ocean, and sea surface temperatures near the coast can influence the air above. When low-pressure systems move along the coastline, They may strengthen if upper-level support, moisture, and temperature contrasts align. El Niño can affect the likelihood of certain storm tracks by altering the larger flow, but Atlantic conditions and continental air masses shape each event. The East often experiences impact through storms that have been reorganized over land or along the coast, not through a direct Pacific system alone. The Appalachian Mountains influence precipitation and temperature patterns. Moist air moving toward the mountains can rise, cool, and produce rain or snow on windward slopes. On the other side, descending air can become drier. The mountains can also help channel cold air near the surface, especially during winter storms. Cold air damming occurs when dense cold air becomes trapped against the eastern side of the mountains, while warmer air moves above it. This can create freezing rain or mixed precipitation in some areas. El Niño may affect the broader storm frequency, but these local mountain effects determine the form of precipitation. The Great Lakes add another layer of complexity. In winter, cold air crossing open, lake water can pick up moisture and produce lake-effect snow downwind. A milder El Niño winter in parts of the northern United States can reduce the persistence of cold air and influence ice cover. But lake-effect events can still occur when the right air mass arrives. If the lakes remain relatively open, they can supply moisture during cold outbreaks. The result depends on temperature, wind direction, lake warmth, and ice conditions. The El Niño signal is present only as part of the larger seasonal setting. In the southeast, wetter cool season conditions can affect rivers, soils, agriculture, and urban drainage. Frequent rain can help reduce drought, support winter water supply, and replenish wetlands. Excessive rain can saturate soils, delay fieldwork, and raise flood risk. Coastal areas may face heavy rain combined with tides or onshore winds. Farther inland, broad rain shields can fill rivers over several days. The region's response depends on how often storms pass, how much moisture they carry, and whether the ground has time to dry between events. In the mid-Atlantic, El Niño winters often bring attention to coastal storms and mixed precipitation. The region lies near a common boundary between warm, moist air to the south and cold air to the north. When storms track along this boundary, precipitation type can vary over short distances. Snow may fall where cold air is deep enough. Rain may dominate near the coast or south of the warm front. Freezing rain can occur where shallow cold air remains near the ground while warmer air moves overhead. These details are determined by vertical temperature structure, not by the climate pattern alone. In the northeast, the signal can be more variable. Some El Niño winters are snowy in parts of the region, while others are milder with more rain or fewer cold periods. The outcome depends on whether storms track close enough to the coast and whether cold air is available when moisture arrives. A strong southern jet can provide storm energy, but snow requires cold air. If the larger flow limits deep cold, storms may bring rain to coastal cities and snow farther inland or at higher elevations. If cold air is in place, the same storm path can produce significant snowfall. The eastern United States also contains many major rivers and urban corridors. The Ohio, Tennessee, Savannah, Potomac, Susquehanna, Hudson, and other river systems respond to regional precipitation, snowmelt, and soil saturation. Cities from the southeast to New England depend on storm drains, transportation networks, power systems, and coastal defenses. A wetter El Niño pattern can expose drainage limits, especially where heavy rain falls over paved surfaces. Winter storms can disrupt travel when precipitation changes form from rain to ice or snow. These impacts arise from the meeting of large-scale circulation and local infrastructure. Temperature patterns in the east depend on cloud cover, storm track, and the supply of cold air. El Niño can tilt parts of the northern and eastern United States toward milder seasonal averages, but this does not remove winter. Cold outbreaks can still occur, especially when the upper air pattern allows Arctic air to move southward. A mild average may include short periods of sharp cold. Likewise, a wet seasonal tendency may include dry intervals. Climate signals are best understood as changes in likelihood across time, not as continuous conditions. Coastal flooding is also a concern along parts of the east. Strong low-pressure systems can drive water towards shore, produce large waves, and slow drainage from rivers and estuaries. Sea level rise has increased the baseline for coastal flooding in many locations, so storms may reach flood thresholds more easily than in the past. El Niño can influence storminess during some seasons, while local tides, winds, coastline shape, and storm track decide the immediate outcome. This combination of long-term change and seasonal variability makes coastal planning more complex. Scientific understanding supports broad tendencies, but it also recognizes limits. El Niño is one of the strongest natural drivers of seasonal climate variation. Yet the eastern United States receives its influence through several layers of atmosphere and geography. Other patterns can reinforce or oppose it. The North Atlantic circulation, polar air outbreaks, snow cover, and random weather variability all contribute. A forecast that identifies elevated risk is useful, but it cannot describe every storm months ahead. The East is a region where the final details often emerge only as individual systems form. In this 14th region, the El Niño signal has travelled to the last broad part of the country. It appears in coastal storm tracks, mixed precipitation zones, river basins, lake effect patterns, and southeastern rains. The influence is present, but it is filtered by the Atlantic, the Appalachians, the Great Lakes, and the many boundaries between warm and cold air. The eastern United States receives the distant Pacific pattern as a softened but still meaningful shift in the atmosphere. It is the final reach of the continental pathway, where broad climate motion becomes regional winter weather. Within homes, workplaces, schools, farms, clinics, and neighborhood streets, the broad El Niño pattern becomes a set of practical conditions. The scale is now smaller than ocean basins, jet streams, and regional storm tracks. It is the scale of rooms, roofs, drains, roads, yards, fields, and daily decisions. A strong El Niño does not enter these places as a named climate event. It appears as rain on windows, damp soil near foundations, snowmelt in gutters, wind against walls, higher water at the edge of a street, or a forecast that changes ordinary plans. The local impact begins with exposure. Exposure means the presence of people, buildings, roads, or systems in places where weather can affect them. A house on a hillside faces different concerns than an apartment on higher ground in a dense city. A farm in a low field faces different concerns than a warehouse beside a dry river channel. A coastal home faces different conditions from an inland home. El Niño may shift the odds of wet or stormy weather, but exposure decides what is in the path of those conditions. The same rain can be harmless in one place and damaging in another. Vulnerability is another part of the local scale. Vulnerability means how easily a person, structure, or system can be harmed when exposed to a hazard. A roof in good condition handles rain better than one already weakened. A drainage ditch cleared of debris moves water more effectively than one blocked by leaves and trash. A household with flexible travel options can respond more easily to flooded roads than one with fewer choices. These differences do not come from El Niño itself. They come from the condition of the built environment and the resources available before weather arrives. Heavy rain is often the most direct household concern during an active El Niño influence pattern. Water follows gravity, collecting on roofs, running through gutters, moving across pavement, entering low points, and filling streams. If rainfall is steady and moderate, soil and drainage systems may manage it. If rainfall is intense, water can exceed capacity. Basements, crawl spaces, underpasses, and low streets are common places where water gathers. Urban areas are especially sensitive because hard surfaces reduce infiltration. Infiltration is the movement of water into soil. When infiltration is limited, runoff increases. Wind can also turn a broad storm pattern into local risk. Strong gusts can move loose objects, break branches, and affect power lines. Saturated soil can make trees less stable because roots hold less firmly in wet ground. In coastal areas, wind can push water toward shore and raise waves. Inland, wind can reduce visibility in rain or snow and make travel more difficult. The wind that reaches a building has passed through large atmospheric currents, but its local effect depends on tree cover, terrain, building height, and maintenance. Temperature matters inside the local scale as well. A milder winter pattern in some regions can reduce heating demand, while cooler, wetter conditions in others can increase dampness and affect comfort. When cold air and storm moisture overlap, ice and snow can affect roads, roofs, and power systems. Ice is especially disruptive because a thin layer can make walking and driving hazardous. Snow can be manageable when expected and cleared, but heavy wet snow can stress tree limbs and power lines. El Niño changes the chances of certain patterns, not the need to follow local weather forecasts. For farms and gardens, local impacts are measured in soil moisture, field access, plant stress, and timing. Rain after drought can restore moisture and support growth. Too much rain can leave roots without enough oxygen, increase erosion, delay planting, or spread plant disease. Warm spells can affect dormancy in some plants, while later cold snaps can cause damage if growth begins too early. Livestock may need dry shelter, stable footing, and access to feed during prolonged wet periods. These outcomes depend on daily sequences of weather more than on the seasonal label. Water systems bring the outside pattern into homes and communities. Storm drains, culverts, retention ponds, levees, reservoirs, wells, and treatment plants all respond to rainfall and runoff. A community with well-maintained drainage can reduce flooding from moderate storms, while overwhelmed systems can fail during intense rain. In dry regions, additional rain may improve water supply, but rapid runoff may not recharge groundwater efficiently. Groundwater recharge depends on soil, rock, vegetation, and the pace of rainfall. At the smallest scale, water security and flood risk can exist in the same season. Health concerns can also arise quietly. Damp indoor conditions can support mold growth if water enters buildings or humidity remains high. Floodwater can carry contaminants from streets, drains, or damaged systems. Heat waves may still occur in a warmer climate background, even during seasons influenced by El Niño, though their timing depends on region. Air quality can change when storms clear pollution or when dry, windy periods raise dust. The health effect is therefore not one single hazard. It is a combination of moisture, temperature, air, water, and access to services. Transportation is one of the ways local life feels distant climate signals. Rain reduces visibility and traction. Flooded roads can hide depth and damage. Snow and ice slow travel. High winds can affect bridges, high-profile vehicles, and flights, rail lines, ports, and supply routes can be delayed by storms. These interruptions may be temporary, but they show how climate patterns become practical through infrastructure. A shifted storm track over the ocean may eventually appear as a missed delivery, a closed road, or a longer commute. Communication matters because seasonal forecasts and daily forecasts serve different purposes. A seasonal forecast can say that wetter conditions are more likely in a region during an El Niño winter. A daily forecast can identify a specific storm, expected rainfall, wind, timing, and local warnings. Preparedness depends on both scales. The seasonal outlook raises awareness, while the short-term forecast guides action. Scientific accuracy requires keeping them separate. El Niño is a background influence, not a direct prediction for every day. At the local scale, uncertainty should not be mistaken for absence of risk. A forecast can be uncertain and still useful. When a strong El Niño increases the chance of certain hazards, communities can check drainage, review flood maps, plan for travel disruptions, and protect vulnerable infrastructure. These actions do not require certainty about each storm. They respond to elevated likelihood. The aim is not alarm. It is readiness based on measured evidence and known exposure. The inner region of the topic is therefore human and practical, but it remains connected to physics. Ocean warmth changes tropical convection. Convection changes upper winds. Upper winds shape storm tracks. Storm tracks bring rain, snow, wind, and waves. Terrain, rivers, buildings, and households turn those conditions into lived effects. The chain is long, and each link contains uncertainty, but the connection is real enough to guide preparation. In this smallest scale, the extreme El Niño warning becomes quiet attention to water, wind, roads, roofs, and the ordinary systems that keep life steady. The pattern settles into a wider view. The ocean remains warm in the places that matter most for the season, and the atmosphere continues to answer in moving air, cloud, pressure, and rain. Nothing in the system stands alone. The surface water holds heat from sunlight. The winds loosen or strengthen. The clouds rise where moisture gathers. The upper currents bend across the Pacific and guide storms toward land. Across the United States, the signal becomes regional and then local, shaped by mountains, rivers, coasts, fields, cities, and homes. A strong El Niño is not a single storm and not a single outcome. It is a climate pattern that changes likelihoods over weeks and months. Some places may see heavier rain, some may see milder air, some may see snow, flooding, high surf, or long cloudy periods. Other places may feel only a small shift from ordinary variability. The science remains careful because the atmosphere is always moving, and each season carries its own details. The calm lesson is connection. A change in the tropical Pacific can travel through water, wind, and cloud until it reaches streets, reservoirs, slopes, and rooms. The warning is therefore not a promise of damage, but an invitation to understand the chain. The planet keeps moving through its slow exchanges of heat and moisture. The ocean stores, the air carries, the land responds, and people prepare within the quiet uncertainty of weather.